Okay, good morning, everyone. Today's class, the sixth lesson of fourth module, and in this module, we are dealing with shear strength. In fact, this is lesson number 7. Okay, so we'll be solving numerical problems uh, based on the concept of shear strength, shear parameters from this class onwards. Um, a lot of problems involve drawing graphs. So please, if you have graph sheets at your home, you can have graph sheets, because in exams also you have to draw this in the graph. Or if you don't have a graph, please draw it neatly with the scale. And most of the problems we will be solving are based on the laboratory tests that are conducted to determine the shear strength or shear strength parameters. So write down the first problem. Today we'll be solving numerical problems based on direct shear test. So write down the first problem. I hope the first problem is visible to all of you. The following data were obtained in a direct shear test. Full stop. Normal pressure is equal to 20 kilonewton per meter square. Tangential pressure is equal to 16 kilonewton per meter square. Angle of internal friction is equal to 20 degrees. Cohesion is equal to 8 kilonewton per meter square. Represent the data by Morse circle and compute the principal stresses and direction of principal planes. So after you write the question, please raise your hand so that we can start solving the problem. Please write down the question and then raise your hand. The problems we are solving today or in this module, they are very important. You will need these concepts in your 6th semester also. And also I told you most of the tests conducted to find the stability or the bearing strength. Okay, most of the calculations to find out certain values, you need to conduct these tests in laboratory. Okay, we'll go to the solution part now. Okay, before I start the solution, I'll just explain the direct shear test. In the direct shear test, we have this shear box. Shear box has two parts, upper part and lower part. And the sample is housed inside shear box. This is our soil sample. And a constant normal load is applied. Okay, for the first trial, from the start to beginning of the first trial, normal load or normal stress is constant. And we go on increasing the shear force. Now you have to remember the normal stress that we are applying, it is constant for for that particular trial throughout the test. Constant throughout the trial. Now the shear force we are increasing from 0 and 0 to failure. Okay, at the end of each trial, we will get, for this normal stress, we will get the particular shear stress at failure. So in this particular trial, 20 kilonewton per meter square normal stress was applied. And for this normal stress, we go on increasing the shear force from 0. We will increase it till the point the sample fails. Now the sample has failed at a tangential pressure or shear stress of 16 kilonewton per meter square. So this is our direct shear test. Now here, what they have already given under what normal pressure the soil failed at, how much shear force or shear stress. But they have to conduct 3 trials to find the shear parameters. They have also given us the angle of internal friction and cohesion. We have to represent all these values in a graph. So we'll plot the graph, always graph. Y-axis is shear stress and x-axis is normal stress. So x-axis is normal stress, y-axis is shear stress. I told you how to draw Morse envelope or strength envelope. Morse envelope or strength envelope. Okay, it is a if this is the Morse envelope or strength envelope. Okay. Its y-intercept is nothing but the cohesion. And it's the angle of the line is angle of internal friction. So they have already given what is the value of cohesion. So in my graph, okay, 20 is the maximum value. So in the graph, I'll take 1 centimeter is equal to 1 centimeter is equal to let's say 2 kilonewton per meter square. So I'll take this scale, and please remember the scale on the x-axis and y-axis must be same. This is very important. You cannot take different scales on both the axes. The scale on both the axes must be same. This is very important when you're drawing the graph. If you keep different scale for y-axis, 1 centimeter is equal to 2 kilonewton per meter square. For x-axis, 1 centimeter is equal to 1 kilonewton per meter square. The answers you will get will be wrong. The most important point when you are drawing graph, okay, the scale on x and y axis must be same. If 1 centimeter is equal to 2 kilonewton per meter square on x axis, then on y axis also you must have the same scale. This is very important point. So 1 centimeter is equal to 2 kilonewton per meter square. So C is equal to 8 kilonewton per meter square. That's why in the shear stress axis, that is y-axis, at a distance of 4 centimeter. I'll mark a point. Okay, so this is y-intercept, that is C. C is equal to 8 kilonewton per meter square. And 1 centimeter is equal to 8 kilonewton, 2 kilonewton per meter square. So 8 kilonewton per meter square will be 4 centimeter. So 4 centimeter distance, I'll draw this. I'll mark the point. Next, after marking the point, I have to draw strength envelope. So I'll hold the protractor. I need protractor also. I'll hold the protractor, and at 20 degrees, angle of internal friction is 20 degrees. At an angle of 20 degrees, I'll draw this line. Okay, so this is my Morse envelope or strength envelope. Okay, did you understand up to this point? Very simple. You have to mark on y-axis, you have to mark 8 kilonewton per meter square point. And from that point, you have to draw a line at an angle of 20 degrees with respect to horizontal or x-axis. So this is my strength envelope or Morse envelope. Next, I have to plot this, okay, normal pressure and tangential pressure, that is shear stress on the graph. Now, normal pressure is 20. So I'll mark that point here. Normal pressure is x-axis. So from 0, I'll measure 20. 1 centimeter is equal to 2 kilonewton per meter square. So 20 kilonewton per meter square will be 10 centimeters. So I'll mark a point that is equal to 20 kilonewton per meter square. Okay, next, tangential pressure, that is shear pressure, is 16. 16 is double of 8, that is 8 centimeters. So somewhere here. So this is 16 kilonewton per meter square. So normal pressure is 20. I have marked that point here, and shear pressure is 16. So next, I'll mark that point. So I'll take a horizontal projection here, and that point will come on the line. So from here, I'll drop if you draw according to scale, you will get that point on the line. So this is my point whose coordinates are sigma is equal to 20, comma tau is equal to 16. So this is the point where the sample has failed. Okay, now I have to draw more circle. It has to be tangential, and the diameter has to cut the from this point I'll drop a perpendicular. Okay, let this point be F. I'll mark this point as F, and from point F I will drop a perpendicular to Morse envelope. So till it touches the x-axis. So this is 90 degrees perpendicular. From point F, that is at the failure point 20, 16, I'll drop a perpendicular and I will get point C. So C is the center point. C is the center point of the Morse circle, and from the center point of the Morse circle, with C as center and CF as radius, I'll draw the circle. Okay, with C as center and CF as radius, I'll draw a Morse circle. Okay, with C as center and CF as radius, I'll draw a circle. I'll get Morse circle. So I'll draw a circle If you have compass, you can draw so this is Morse circle with CS center and CFS radius. Draw a circle. So this is my Morse circle, and this point is sigma 3. So this is sigma 3. This point sigma 3, and this is sigma 1. Principal stresses. Minor principal stress sigma 3, and this is major principal stress sigma 1. Okay, so they asked us to represent the data by Morse circle. So we have represented the data by Morse circle, and they also asked us to compute principal stresses. So sigma 3 principal stress and sigma 1, sigma 3 and sigma 1 principal stresses, minor and major. So if you measure the value, you will get sigma 3 around 9.2 and sigma 1 around 42.5. And they have also asked us to measure the direction of principal plane, meaning the angle of the failure. So you can find the direction of the principal planes from the graph also. So I'll tell you how to find the direction of the major and minor principal plane. Now, from the failure point, draw a horizontal line. This is the failure point. I'll draw a horizontal line from this point. Next, I'll mark this point. Next, from the minor principal stress, I'll draw another straight line. From minor principal stress to this point, I'll draw a straight line. And again, from this point to the major principal stress, I'll draw one more straight line. And this is the minor principal stress. So this angle is the angle of minor principal stress. Let's say angle beta. Beta is the direction of minor principal plane, and this angle, let's say gamma. Gamma is the angle of the direction of major principal plane. Okay, beta is inclination or direction of minor principal plane. And we also have gamma, which is direction of major principal plane. So if you can find these angles by using a protractor. Okay, if you just draw these lines and keep a protractor at this point, you can find the angles of beta and gamma. So I'll tell you the answers. You please try this. Maybe some of you have not, you don't have the graphs right now, but from the next class onwards, if you have graph sheets, please be ready with your graph sheets so that you can plot it and understand it much better. And if you have any doubts, you can ask now itself. I'll just write down the answers. Sigma 3 is sigma 3 is sigma 3 is 9.2. And sigma 1 is 42.5 kilonewton per meter square. Next, beta is the inclination of minor principal plane. Now this beta is equal to 35 degrees. Beta is equal to 35 degrees, and inclination of major principal plane is 55 degrees. So these are the answers. We are asked to represent the data by Morse circle. We are representing it by Morse circle, and we are asked to compute principal stresses. So principal stress, minor principal stress, sigma 3 is 9.2. Major principal stress, sigma 1 is 42.5. Direction of principal plane. Okay, direction of minor principal plane is 35 degrees. Direction of major principal plane is 55 degrees. If you have understood, just raise your hand. If you have not understood, if you have any doubts, you can ask.
Sir, why didn't you join at F, sir? Sigma 3 and Sigma 1. Why did you extend that line?
No, these are graphical methods. Okay, they have this is Morse circle. The experiments are conducted, and through the experiments they find out what is the inclination of major principal plane and what is the inclination of minor principal plane. And from the minor principal plane they have drawn a line at that particular angle, and it has it is intersecting at this point. So at this point only you have to draw the line, and then you have to find the inclination. You can solve it using analytically also. Okay. You can solve it analytically, and then you can plot this graphically. You will get the same answers. Okay, these are all trial and error graphical methods. They have correlated the laboratory experiments with these graphs, and they have correlated the analytical stuff with the graphical solution. So you will get the inclination at this point only. You won't get at point F. All this graphical solution, first they have done the analytical stuff. Okay, they have done mathematically, they have done analytically, and then they have converted these into geometry or graphical solution. So always first thing is analytical, and then they go to graphical solution. They go hand in hand. Okay. Again, I have class again at 12 o'clock. Okay, Rekha madam is not taking class. I'll be taking that class at 12 o'clock. So we'll continue this class at 12. Okay, we'll go very slowly because the last working day is also very far. So again, at 12 o'clock, we'll solve one more problem. If you don't have any graph sheets now, please make sure you have graph sheets. Today, I'll be checking if you have to upload, because these problems are very important. I told you, if you want me to point one unit or one module or one concept which is very important, it is this concept. So you have to upload all the stuff you have done in this class into the Teams. Okay, so if you don't know how to where to upload, I'll just show you. Everything we have done today, you have to upload. Just go to Teams, and in Teams, go to 5th semester, 5 _ civil. Don't go to this new channel. Go to here, 5 _ civil, and in 5 _ civil, go to basic geotechnical engineering channel. Here we have files, and in files we have different folders. I'll just create one more folder. Sorry. Shear strength of soil. November 30th. I'm creating this folder here, so you can upload. You can just scan, make a PDF and upload in this folder. Please solve these problems. Don't just listen to the video or log in, mute and go do your work. This is very important, even if, because all these concepts you will be doing it again in the next semester. If you don't understand this, you will find next semester very hard. The GT subject in your next semester very hard, and also you have lab in your 7th semester. If you don't understand this, you won't understand a single thing in your lab. And all these concepts, we are using it in practice, in the field, in the office, or whatever. So these are very important concepts. So if you have logged in, kindly pay attention and please gain this knowledge. Okay, we'll meet again at sharp at 12 o'clock. Okay, we'll solve some more problems. Till then, you can try to solve this problem in the graph, and if you have graph sheets, please be ready with your graph sheets at 12 o'clock. We'll only solve one problem then. Okay, so thank you for attending this class. We'll meet again at 12. Thank you.